Greetings folks, and welcome to this lecture video. Here we will learn what repeated fixed delay executions are and how to use the Threads API to schedule tasks for the same. As discussed previously, timer and timer task classes only are used for repeated executions using the Threads API, whether for fixed delay or fixed rate. The timer class provides two overloaded methods for this purpose. Both take three arguments in which the task and the period arguments are the same. Period represents the interval between two adjacent executions of the task. The third argument is either a date or a milliseconds offset from the current time that indicates the start time for the first execution of a particular task. Once the timer executions start, subsequent executions take place at approximately regular intervals separated by the specified period. Now, here is an important point to remember. In repeated executions, the next execution of the task is scheduled when the current execution begins. That is, every time a task starts to execute, the timer class calculates the next execution time for this task and schedules it accordingly. If you look on the internet, you will find many answers on what fixed delay executions in Threads API are, and majority of them are wrong. Most of them state that the next execution is scheduled relative to the completion time of the previous one. That is, the next execution starts after the current one has finished and the time interval between the completion of the previous one and start of the later one is as specified by the period argument. The language used in Java docs is also ambiguous. It states that the next execution is scheduled relative to the actual execution time of the previous one. People get confused with the phrase actual execution time. Heck, I got confused by that too. What do they mean by execution time? It seems to refer to the duration between start and end time, but that doesn't make any sense. Well, what they actually mean by that phrase is that in fixed delay executions, each execution is scheduled relative to the actual start time of the previous execution. But do recall from our previous video that scheduled time of an execution and its actual start time may differ by a few milliseconds sometimes. So it follows that if an execution is delayed for any reason, then all the subsequent executions will be delayed as well. And you will notice a drift in the start times over long runs. Secondly, sometimes you may observe that the first run of the task is also scheduled a few milliseconds later than what was specified. Now, the timer class doesn't give any real-time guarantees. In general, if a task is scheduled to run at time X, then due to some overhead or other reasons, it may many a times start a little later than X. Hence, in the long run, the frequency of executions will be slightly lower than that specified while calling the schedule method. For example, if you specify that the task should run every 2 seconds, then its frequency is 31 times per minute. However, in the long run, you will observe that the frequency comes out to be lower than 31 times per minute because of some milliseconds difference between the scheduled execution time and the actual execution time. And I have already mentioned that the next scheduled execution time is calculated relative to the previous actual execution time. So, if the current actual execution is delayed, then the next scheduled execution time will also be delayed. Then the next actual execution time will be either the same as or later to the next scheduled execution time. So, over long periods, this cumulative delay becomes significant and results in the frequency of executions to become somewhat lower than what was initially specified. Now, the fixed delay execution is appropriate for recurring activities that require smoothness. An activity appears to be smooth to a human eye if its frequency stays relatively constant in small runs. So, this scheduling is appropriate for activities like blinking a cursor at regular intervals and automatically repeating a character as long as a key is held down. Let's write some code now. This is our main class, And for tasks, we will just use the scheduled task A that we developed in the previous lecture. In the main class, we will create a timer and then schedule a task for repeated fixed delay executions using one of the overloaded methods that we saw a couple of minutes ago. We will let the timer run for some time and then cancel it. That was easy. Here we have used a version of schedule that takes a date object as parameter. We have scheduled the task to run every 2 seconds and the task takes 1 second to execute completely. So we expect no hogging of the execution thread here. Let's run it now. We see that it prints the current time first, which is 20:32 and 51.074 seconds. The first run was scheduled at 20:32 and 54.074 seconds, which is 3 seconds after the current time. And it actually started at exactly the same time as the scheduled time. And then it finished 1 second after it started at 55.087 seconds. The next scheduled time was 56.079, which is around 2 seconds later than the actual execution time of the previous run. And then it ran also at the same scheduled time, and so on and so forth. Now we can schedule any number of different tasks for repeated execution using a single instance of timer. Just be a little careful that the executions of the two tasks do not overlap each other, because we have just a single thread in the timer that executes all the tasks. And if the single thread is doing the executions, then obviously the executions will be done sequentially. So the actual execution of the second of the two overlapping tasks may be delayed by a large offset if the first one is long running. As I said in the previous tutorial before, it may be more prudent to schedule different long-running tasks in different timers. That being said, let us still try to run a second task repeatedly using the same timer instance here. This time we have used the other version of the overloaded schedule method that takes a millisecond offset parameter instead of a date. This second task will start after an initial delay of 4 seconds and then execute approximately every 2 seconds after that. The task running length is the same as that of the first one, 1 second. Running it now. Let's wait for it to finish. Okay, it's done. So first of all, it has printed the current time, that is 20:41 and 9.133 seconds. The task 1's first run was scheduled at 20:41 and 12.134 seconds, which is around 3 seconds after the current time, and it actually also started at the same as the scheduled time. Then it took 1 second and then finished. The task 2's first run was scheduled at 20:41 and 13.136 seconds, which is approximately 4 seconds after the current time, and it also started at exactly the same time as it was scheduled for. And then it took 1 second to finish. Then the task 1 ran again, and its scheduled execution time was 20:41 and 14.225 seconds, which is approximately 2 seconds after the previous actual run time. And task 2's second run was scheduled at 20:41 and 15.240 seconds, which is approximately 2 seconds after its previous actual execution time, and so on and so forth. And that's it for this tutorial. Thanks for watching it. See you in the next one now, where we will discuss the repeated fixed rate executions. Till then, take care and bye.